Welcome back. This is the fourth in a series of several lectures for chapter 26, which deals with refraction and convex lenses. So let's start with convex lenses. A convex lens, also known as a converging lens, you may know it by its other name, magnifying glass. A convex lens bulges out on both sides. I show here two special light ray behaviors, the way these special rays of light behave as they pass through the lens. Shown here is the axis of the lens. It passes through the center. Any ray that is incident on the lens and is parallel to the axis is called a paraxial ray, parallel to the axis. That's shown here, that ray parallel to the axis. What happens to all paraxial rays is what's happening now to this one paraxial ray. It is bent after it passes through the lens and travels through a point on the axis labeled F, which stands for focus or the focal point. Focal point, focus, same meaning. A second important ray, a so-called special ray, is shown here. It's a ray of light that is aimed at the center of the lens. Any ray that's aimed at the center of the lens goes through the lens without being refracted, without being bent. Now, these two special ray behaviors can be used to determine the characteristics of the image that is formed when an object is viewed through a convex lens. I show a convex lens, and on the axis, I use that arrow to represent any object whatsoever. It may be something as small as 8 millimeter tall newsprint, or it could be, you name it. It's the object, and it has an image. Let me describe now how the image is formed. We have on the right side of the lens, on what I call the eye side of the lens, the observer's eye, not drawn to scale, obviously. We have this object in sunlight or room light, overhead lights, light from the sun or overhead lights, lands on the top of this object arrow and is reflected in an uncountable number of different directions. We're only going to follow those two rays shown here, one of them being a paraxial ray that, as we have just seen here, bends through the focal point, which is here. The other ray that we choose to follow passes through the center. It keeps on going, is not bent. The intersection of those two rays is perceived by this observer's eye to be what might just as well be an object there from which light is emanating. You see there is light traveling along that path to the eye, and from that point along that path to the eye, it is just as if there were an object there from which light is emanating. But in fact, this brain, clever enough, it knows that there's not really an object there. The actual object is over here. This is named the image. And notice the characteristics of this image. It's shorter than the object. We'll just call it smaller. It's upside down. The technical name is inverted. And because light really is coming from that place in space where the image is said to be real because there really is light coming from that location. Now, there are some parameters, quantities that relate to this diagram that are used to calculate exactly how tall or short the image is, whether the image is inverted or upright is the other word, and whether the image is real. The same diagram here is redrawn over here. There's your lens, there's the observer's eye, and there is the object arrow. I indicate the height of the object, H subscript O, and I show the image here. Its height is H subscript I. Know this, that images that are upside down will have heights, so-called, that are, well, they're negative. Object heights in all of our treatments are always positive. The distance of the object from the lens, distance between these 2 points, is labeled X. X is a positive number. The distance between the lens and that point there, which is the focal point, is called the focal length. Focal length is a positive number. The image is located here, a distance y from the lens. Now, unlike x, which is always a positive number for all of our lens situations, and f is always a positive number, on occasion, y, the so-called image distance, can be negative. In this case, the image distance is positive. You would have no way of knowing that it is positive, but we'll make that clear soon enough. If in another situation the image appeared on the other side of the lens, on the side of the lens that's not where the eye is, then in that case, as you will see in another example, y would be a negative number. So I'll state a rule now, maybe a couple of rules, and repeat them later. If the image is on the eye side, as is the case here, the image distance y is positive. I'll make that point over and over and over as we go forward, not in this particular part, however, which is part 4, by the way, of chapter 26 lecture videos. On the other hand, if the image is not on the eye side, y is negative. And I can say more than that. About the nature of the image, whether it's real or not, we have this I can tell you, that if the image is not on the eye side, then the image is not real. I'll repeat it multiple times throughout this sequence of lectures. If the image is not on the eye side, it's not real. Furthermore, if the image is not on the eye side, the value of y, the image distance, is negative. I'll have more to say about images being real versus not real in another part, a coming lecture. The last thing I'll tell you before we move on to a different part is that there are some crucial equations, very important equations that we can use, you can use, to determine the characteristics of an image, such as whether it's on the eye side of the lens, whether it's shorter or taller, whether it's upright or inverted, and whether it's real or not real. The equations I'm referring to are shown here, the so-called, by me, reciprocals equation. Kind of reminds you of the reciprocals equations that we saw in electrical circuits for equivalent resistances for parallel. Well, let's not get into that. The reciprocal of x plus the reciprocal of y equals the reciprocal of the focal length. M stands for the magnification. Somewhat of a misnomer because the magnification value could be a fraction and it can be even negative. It's negative y over x. I will not derive or prove that to you, and nor will I prove to you the reciprocals equation. We're just going to learn how to put them to use to discover the attributes of images that are formed when we're looking at an object through a convex lens. And finally, an alternative way to calculate the magnification of your image is to form the ratio of the various heights. H sub I is the image height, H sub O is the object height, and I will say this, object heights are always positive by definition, but image heights, well, they can be negative, they can be positive. You could have, for example, an image height that's negative 5 centimeters, or positive 3 centimeters, or 0.3 centimeters, or negative 0.6. You get the idea. So there's two magnification equations and one reciprocals equation. There is yet to follow, but not in this part, a very valuable alternative magnification equation that I will derive for you. Exciting times ahead. All right, that does it for part 4, chapter 26. I'll see you next time.